Hello, and so this next video is actually going to be a combination of chapter 17, 19, and 25. I'm pulling in the different reactions to try to cover them before the end of the year. So the first reaction that we're going to be covering is the Wittig reaction, stuff like that. So it's used to convert C double bond O's into alkenes, stuff like that, and bring that along. It's a pretty useful reaction. So we're going to take this, wherever that C double bond O is, that oxygen is going to be replaced by the carbon that bears this negative charge. So that's going to be next to this triphenylphosphine moiety here, stuff like that. And so that carbon is going to directly replace it. You're going to leave that double bond in there, and whatever is attached to this to that carbon is going to come along for the ride, and so we can convert this into there. The pH here, that's just a abbreviation for phenyl, so it's just a regular benzene. So like that, and so how this works is that the carbanion here, the stabilized carbanion, right? Because it's Wittig ionic, right? So it has a carbanion stabilized with the positive charge on this phosphorus. So that's going to do nucleophilic attack onto that carbon, pushing that up, right? Because there's a polar covalent bond there. The oxygen is then going to attack the phosphorus. Now the phosphorus oxygen bond is incredibly strong, and it's a big driver for this energetically, stuff like that. So very similarly, if you study biochemistry, the hydrolysis of ATP, that's a big driver in biological systems, and it's because of that formation of new phosphorus oxygen bonds that can help drive this. You come in here, so these electrons collapse. Those electrons come in to make up onto the oxygen, and so you come in and replace the oxygen with that carbon. It's pretty useful. Okay, and so if you're looking at this, right? So that plus triphenylphosphine, right? So here's where that. Right, so here's where the carbon with the carbanion, so that's going to directly replace that right there. So this here, so 1, 2, 3, 4, 5, right? 1, 2, 3, 4, 1, 2, 3, 4, 5, right? 2, 3, 4, 5, stuff like that. So this carbon replaces that oxygen, right, to make that. Okay. So for this one here, it also works for aldehydes, right? Plus triphenylphosphine, so like that. So this carbon here is going to directly replace that oxygen. Right? Double bond remains, and all these other carbons come along for the ride. Stuff like that. So the triphenylphosphine phosphine oxide goes away. Stuff like that. So and so this is what you form here. Okay. So I forgot to mention that this compound here is called an ylide. Stuff like that. So and it's formed by a couple of steps. This is going to be something that you have to generate in situ. Stuff like that. So you can't just buy that from a supplier, but you can buy, say, the bromide where you need to, or make it. So with that, triphenylphosphine is fairly inexpensive. So with that, and so you come in here and that displaces it, and then you need a good base such as butyllithium to come in here and deprotonate it to make the carbanion there. So with that, and so this is just a simple SN2 reaction, right? The phosphine is going to attack here, displace the good leaving group with the bromide to make this, the carbon-phosphorus bond, and then you can come in here, use a strong base to rip off that hydrogen here to make the stabilized carbanion here. It's Wittig ionic, right? So that has what's positive and negative charge. So that's the typical way to do this, right? So if we're going to take a look at this, right? So with that, and so if we end up do the triphenylphosphine, right? So with that, so this first step, right? So with that, so the first step would make you would do an SN2 reaction, right? Plus charge there. The butyl lithium, right? It's gonna take this hydrogen away, right? To leave you with the this ylide here. Okay, so this would be A here. Okay, now this carbon here replaces that oxygen there, and so you end up with the original benzaldehyde, right? And then 1, 2, 3, 4, 5, but it's connecting through carbon 2. So 1, 2, 3, 4, 5. So there we go. Okay, so we talked earlier about the fact that on one of the previous chapters that when you add HBr across the an alkene, right? So with that, so the H is going to go on the less substituted side. That produces the carbocation. You want that carbocation to be on the more stable or on the more substituted side, right? The higher numbered sides, so that the bromide can come in and attack. And so you get this Markovnikov product where the bromine, or in this case, what's not, what's opposite the H, is going to go on the higher numbered side. But the question becomes, what if you really need that bromine to be on this side? So what do you do? And it turns out that if you run the same reaction, but you run it in the presence of peroxide, typically something like hydrogen peroxide, stuff like that. So the it'll actually switch the selectivity of it, the regioselectivity, and in fact put the bromine on the lower numbered side. So it's the complementary reaction. So with that, do you remember we talked about hydroboration versus oxymercuration? The hydroboration, you put the OH on the lower numbered side, and the oxymercuration, you put the OH on the higher numbered side. So you get the complementary. Same thing with this one. You have the depending on with and without the peroxide, you can get selectivity on that. And the reason it does that is the fact that it actually changes the mechanism. It runs through a radical, stuff like that. So the bromide actually gets added first, and so the tertiary radical is going to be stabilized here. So since the bromine gets added first, it's going to go on the lower numbered side, and so the hydrogen can then come in and add to the higher numbered side. So then the question becomes, well, what if you want to preserve this this double bond, right? It's synthetically useful, but you want to use the you want to say put a bromine here, keep that bromine there. What you can do is you can use a compound called N-bromosuccinimide, which is right here, stuff like that. And so what it does is it puts it breaks a CH bond. You have to have a CH bond next to a double bond. Now, it doesn't matter if it's an alkene like this, or if it's a benzene like this, right? There's still a double bond here, and so it can replace it right there. Okay, so with that, so if X is in NBS, only one bromine gets added per site, stuff like that. So you're not going to get like a whole bunch of bromines here and a whole bunch of bromines there. You add one and then it stops. Okay, stuff like that. But if you notice on this compound, okay. Like here, right? So this is a CH2, okay? So we can add it here, okay? This is a CH3, okay? So we can add it here, but this site here, right? It's still next to this double bond, but it only has carbon-carbon bonds on it, okay? And so because it doesn't have any CHs, this is going to be resistant, and so it's just these two sites that get attacked, get replaced with the bromine. Okay, and so if we're looking at this, right? Okay, we're adding HBr and peroxide, H2O2. Okay, so we're going to add HBr across that double bond. We're going to put Br on the lower numbered side, and so this side, right? So we have two carbons attached to it, so it's secondary, this one here, this one only has one carbon attached, so this is primary, and so we're going to put the bromine on this side. Like that. And then that stays there. So, and then here's CF3. Right, so like that, and so MBS. That's supposed to be a double bond here. And so you look on, you look here and here. Okay, so this doesn't have any CH bonds, right? So these are carbon fluorine bonds. Okay, and here you have CH bonds. Okay, so CH2. So you're only going to be, so you can't add here, so you're going to add right there. So CF3. Put a bromine there. Yep. Like that. Okay, so next thing I want to talk about is what's called the Wolff-Kishner reduction, stuff like that. And so this one, what it does is it blows apart an oxygen, a C double bond O, from an aldehyde or ketone. It destroys it and just converts it into a CH2 and stuff like that. And so this is done with NH2 hydrazine in the presence of KOH. You heat this up and away it goes, because you end up releasing nitrogen gas, which is the big driver for this, and stuff like that. And so you literally can just go in and say, okay, it's just going to remove that. Like that. Okay. So it works pretty well. The other way that you can do this is what's called a Clemmensen reduction. So like that. So this one uses zinc mercury in the presence of acid, and it does the exact same thing, right? So it's going to rip apart it's going to take out the oxygen of a C double bond O and just convert it into a CH2. So like that. And so the reason why we have both of these is the fact that this one is run in acid while this one is run in base. And so you have to look at the other, so when you're designing these to pick it out, you have to make sure that your other groups in the molecule are either acid tolerant or base tolerant, stuff like that. So if they're labile towards it, right, they're reactive to acids or base, you have to use the other one. So like that. So it gives you some flexibility on this, but they do essentially the same thing. Stuff like that. And so here we go. So if we have cyclohexanone, right, do NH, the hydrazine and KOH, right, so like that. So we're gonna just knock that out, and so it ends up just cyclohexane. Same thing with this one, right? So with that, so HCl, zinc mercury amalgam. Right, so for that, again, we're just going to take that away. Now I'm going to leave this hydrogen here. You don't need to do this. You don't need to put that in, but just for simplicity's sake. So those are the 5 carbons, right? 1, 2, 3, 4, 5. So like that. So that's all you need to do. So for that, so is take that away. So there you go. Okay, so for catalytic hydrogenation, what we're going to be doing is we're going to be taking alkenes and converting them into alkanes, stuff like that, by putting hydrogen across it. Typically, it's done with hydrogen gas in the presence of some sort of solid catalyst. This is things like palladium that's embedded on carbon. Palladium can be rather expensive and it's reactive, stuff like that. So you embed it into carbon, it's a little bit easier to handle. It's also a lot cheaper. You can also do platinum, nickel, rainy nickel, things like that. Stuff like that. And so but essentially what it does is it converts alkenes into alkanes. It just takes out that double bond. And the way that this thing works is that the hydrogen actually breaks apart and embeds itself into the solid support, stuff like that. So, and then the alkene comes in and it comes down like this onto the surface, grabs 2 of those hydrogens and pulls them away. But the hydrogens get added on the same side. Okay, stuff like that, and so it's a cis addition with those hydrogens. Okay, not too big a deal if it's just a regular alkane, but if it's, say, a cycloalkane that can't rotate, those hydrogens definitely are going to be on the same side. Stuff like that. So this is the same sort of hydrogenation that's done for cooking oils, stuff like that. And so if we talk about partially hydrogenated oils or fully hydrogenated oils, or what they're actually doing is this reaction. And so what they do is you take these these polyunsaturated oils. So they have the chains, they have multiple double bonds, right? So for that, the mono unsaturated would just have one. But these are typically done through, naturally these things are done with cis double bonds, stuff like that. And so that provides a kink in the chain. And so the way that I usually talk about this, the visual, is to think about when you're on a subway, a crowded subway platform, right? Everybody is straight. If these things are completely saturated, I know this is kinked around, but that's just for the space. But if it's fully saturated, it's straight. Stuff like that, and so you can pack a lot of material in there, and you get a lot of people onto that platform. This cis double bond provides a kink, and so if you were to have everybody have like a heavy backpack, and so they are all leaning over, you wouldn't be able to pack nearly as much material into that same space, and stuff like that. And so that's why if everybody's straight, right, stuff like that, so you can pack a lot more. That's why it's a solid, stuff like that. But if you kink it, you can't put nearly as much material. You don't have very good interactions between the molecules. That's why it's a liquid, stuff like that. So that's why the unsaturated are typically more like olive oil, stuff like that. And so, but what can sometimes happen is that these things don't go to completion and stuff like that. And so that's how, and then they revert back to the double bond. But typically, the trans can be a lot more stable, stuff like that, and so it converts into the trans double bond, stuff like that. And so you talk about these trans fats, stuff like that. What happens is it has a trans double bond in it. Instead, your body doesn't know how to handle that very well, and stuff like that, and so it accumulates in the body, stuff like that. So that's what's going on. Now, if you're to do this for alkynes, right? So you convert this to the alkenes, stuff like that. But this is still going to be reactive, stuff like that, and so it's going to get converted down to the alkane. And so if you just do this reaction, regular, right, Raney nickel in presence of hydrogen, it's just going to go all the way to the alkane, stuff like that. So if, however, you wanted to, stuff like that. So I want to come here. These are slightly out of order. Stuff like that. So you can also do this with other types of double bonds. Stuff like that. So you can take this with an aldehyde. You can take this. You can convert that. Put a hydrogen across that double bond to make the CH2 and the OH. You can also do this with with ketones. Stuff like that. So nitriles. Right. So for that, so that you can convert the. You can put two hydrogens across these molecules, right, to make the amine. Stuff like that. So, and even amides, you can do this, convert that C double bond O to just a CH2. You actually end up releasing water from that. It's kind of a quirky little reaction, stuff like that. But if you notice, depending on the reactivity, you have to force the reaction more. So aldehydes are really reactive, so you can just get away with 1 atmosphere. Ketones are less reactive, so you need to bump up the temperature to 50 degrees Celsius and 3 atmospheres. Nitriles, even less reactive, and so now you're doing 80 degrees, 75 atmospheres of hydrogen. When you come down to the amides, which are really stable, they're very unreactive, you need platinum, 250 degrees Celsius, 200 atmospheres, and even then it's not a great yield. Stuff like that. And so you can do this. You can take down other double bonds, but you're going to have to force it because of issues of stability. Okay. Now the question becomes, if in fact you want to just stop at the alkene, okay, stuff like that. So how do you do it? Stuff like that. And so what you do is you actually poison the catalyst, okay, and so that the first step, making the alkene, can go, but the catalyst is so terrible at that point that it's not quite good enough to allow that second reaction to occur, stuff like that, and so it stops at the double bond. And because, remember, we're adding the hydrogens on the same side, stuff like that, we get the cis isomer of that alkene. Okay, so these are typically what's called a Lindlar catalyst, which is just palladium in the presence of some quinone, stuff like that. And the other way that you can see this, palladium in the presence of barium sulfate, stuff like that. So it has barium sulfate embedded into it. That will also destroy it, stuff like that. And so this is a good way to make the cis alkene, stuff like that. So and so for this way, right? So Lindlar catalyst, right? So you're gonna make the cis double bond here, stuff like that. So stuff like that. But the question becomes, well, what if you want to make the trans alkene? Well, you do what's called a Birch reduction and stuff like that. And so you can't just do a hydrogenation, right? Because the mechanism isn't going to work. And so you have to actually change the mechanism. And so you use a you use a radical reaction to do it, and what ends up happening is you either use sodium or lithium in the presence of ammonia, stuff like that. It's a really cool reaction because it turns very dark blue and stuff like that, and so it'll actually convert the triple bond into a trans double bond. Stuff like that. So here's the mechanism. It involves, your alkali metal giving up its electron, right? So it can become into the, so it can go into the noble gas configuration. The double bond will come and absorb it, and then rip off hydrogens from the ammonia itself, to make the amide. Stuff like that. So stuff like that, or not the amide, the ammonia anion. So the and so you don't need to know this mechanism, but what you do is you change the you use a different mechanism to make the trans. Okay, stuff like that. And so if you've got this, right, stuff like that, so you have, right, so you have alkyne, right, stuff like that, and so you're just going to do a regular palladium on carbon, right, hydrogenation that goes completely to the single bond. Okay. If you have the this triple bond here, right? But instead, you're going to use this poison catalyst, the palladium with barium sulfate embedded. Okay, you're going to end up making the cis double bond, right? Because you're going to put those hydrogens, on the same side, right? So you make the cis isomer. Okay. Now this last one here, right? So with that, so. Right, you have a triple bond, right? But you're going to do sodium in the presence of ammonia, right? Now you're going to make the trans, right? Like that. Oop, I'm sorry, the trans double bond. Okay, so like that, and so this one's going to make the trans. Okay, so now this part here, this is the oxidations of alcohols and aldehydes. So this ends up being a little quirky, stuff like that, but it's not hard, stuff like that. So what we're doing is, when we talk about a lot of oxidation reductions, there's a couple of different ways we can do this, and the book goes into this really complicated scheme for how to be able to calculate it, stuff like that. But a good rule of thumb is that if you're adding CO bonds, you're oxidizing. If you add CH bonds, you're reducing, right? So with that, and so you can just calculate just look at how many CO bonds you're making, okay? And so from going from here to here, right, you go from 1 CO bond to 2, right? And if you keep going to the, you do another further oxidation, you burn a CH bond and turn it into a third CO bond, right? So it'd be great if you can make a CO triple bond. That would make sense, but that would be carbon monoxide, and we're not going to have that in our molecule. So by that, so the other way that you can get 3 carbon oxygen bonds on this is through to make a carboxylic acid. Now there are ways of taking a ketone into here. We're not going to get into that. It's called a Baeyer-Villiger oxidation, stuff like that. But if you have if you can burn another CH bond, you can make it into a carboxylic acid. But each time we go in there, so if we're going to do a reduction, right, we're replacing a CO bond with a new CH bond. So like that. So, okay. So hydrogen chromic acid. Okay, this is one. There's also potassium dichromate. This is another one. It's a high oxidation chromium, right? So it converts a CH bond into a new CO bond. Okay, and so I'm just going to just look at this top part. Okay, so CH, right? I'm going to do the chromic acid. Okay, and so what we're doing, if you look at the accounting for this. I'm just going to look at this part, right? So we just look at the carbon that has the CO bond, okay? And so it has 2 carbon-carbon bonds, right? 1 CO bond and 1 CH bond, okay? With chromic acid, what we do is we take all of these CH bonds and convert them into CO bonds, and so our product is going to have, we're going to maintain those CC bonds, but now it's going to be 2 CO bonds and no CH, okay? And so we're going to keep those 2 carbons. Those carbons are going to remain, but now we need 2 CO bonds, and so you end up making a C double bond O. Like that. And so that's how I usually do the accounting for these. Okay, so with that, so but here, notice and here there's no carbons, or there's no CH bonds at that site, and stuff like that. And so you need to at least have one to be able to do it, right? This carbon-carbon, it's 3 carbon-carbon bonds, 1 CO bond. We don't have any currency, any CH currency to be able to burn it. So this is going to be, this tertiary alcohol is going to be resistant to it. Okay, so again, this is potassium dichromate or chromic acid, stuff like that. And so here, right, we're going to have, right, so 1, 2, 3, 4, 5, right, so 2, right, so CH. Okay, so chromic acid. Okay, so we have, right, so we're just looking at this carbon here, because that's the one that has a CO bond, right? It has 1 CC bond, 1 CO bond, and 2 CH bonds. And with chromic acid, right, we're going to convert all of those, all of them up. Okay, and so our product is still going to maintain that 1 CC bond, but now we're going to have 3 CO bonds, 0 CH bonds. Okay, and so we draw in our carbons, right? So with that, so how do we get 3 CO bonds on a carbon? Right, make that into a carboxylic acid. So with that, so 1, 2, 3. Okay, now if you needed to stop at the aldehyde, okay, so what you can do is you can actually use this compound code PCC. So with that, and so that will actually only do one step. Okay, and so if you're looking at, I'm just going to draw the here, right? So I'm only going to draw the cyclopropane here, stuff like that. And so here, right, with the PCC, so this carbon here, right, it's got 1 carbon-carbon bond, 1 CO bond, and 2 CH bonds. Now for the PCC, we're only going to convert one of them up. So our new site is going to have, again, it's going to have 1 carbon-carbon bond, 2 CO bonds, right? So 1 from where it had normally, originally had it, and then just 1 of these CH bonds. And so we're going to have 1 of these CHs remaining, and so the compound is going to have that CH bond, so we're just going to take out 1 of those to make a new CO bond. So with that, and this hydrogen just goes away. So okay. Potassium permanganate, KMNO4, works exactly like the chromium compounds, stuff like that. So it's just chromium is a little bit more selective, but permanganate's cheaper, stuff like that. So, but chromium is also a lot more toxic, stuff like that, difficult to dispose of. Okay, and so for here, right? So with that, so OH, like that. So you want to put in that, draw in that hydrogen, right? So you have H2 chromic acid, okay, and so we have, right, so we're looking at this carbon there, right? We have 2 CC bonds, 1 CO bond, 1 CH bond, right? And so we're going to convert one of these up, or all of them up, so with that, so our new product is going to have 2 CC bonds, 2 CO bonds, and no CH bonds. Okay, so our new product at that site is going to have 2 CO bonds, or 2 CO bonds, right? 2 carbon-carbon bonds. So there's our product there. Okay. This last one. Okay, so with that, NH. Right, so we're interested in this site here. So go ahead and draw on those hydrogens, right? So with that, so KMNO4. Right, so with that, so we have, so that site there that has 1 carbon-carbon, right? 1 CO bond, okay, 2 carbon hydrogens, right? So and again with KMNO4, right, we're going to convert them all. So with that, and so our new product is going to have 1 CC bond, right? So 3 CO bonds and no CH bonds. Okay, so right, so here's our original carbon, right? So how do we put 3 CO bonds on there? Make it into a carboxylic acid. So there we go. Good luck.